Hello everyone and welcome back to Introduction to Deep Neural Network. This is lecture number 3. In the previous video, we have discussed the perceptron. In this video, I'm going to talk about how to combine multiple perceptrons together in order to build or create an artificial neural network that can represent complex functions. We're also going to talk about deep neural network. A single perceptron is good enough to represent a linear mathematical formula, which can be used to represent or solve simple problems. However, representing more complex functions or logic requires the use of more than one perceptrons. Those perceptrons has to be put together in a certain order or topology. In this topology, perceptrons are grouped into layers, as you can see in the figure. The input layer is the layer that holds the input to the solution of the system. The output layer is the one that produces the target output result. Number of neurons in the output layer is related to the function that we are trying to implement. For example, a binary classifier can have only one output, which could be 0 or 1 based on the input. The layers between the input and the output are called hidden layers. Those are the actual computational unit in a neural network. The neural network topology can have more than one hidden layer based on the complexity of the problem to be solved. Each layer processes the same input, but with different weights for each perceptron. The whole neural network at large is used to model an algorithm, a mathematical formula, or a specific task like a regression, classification, or clustering task. When designing a neural network, many parameters need to be considered. As we discussed before, the nature of the problem, the condition of the data. Data could be noisy or clean, and this could affect the behavior of the network. There are different types of hidden layers, which we're going to discuss later. The activation function used also is important. There are different types. Each type should be used in different tasks. Number of hidden layers and number of neurons in each layer is very important because those two elements together represent the complexity of the mathematical formula we are trying to implement. We also should consider the model performance and the target deployment platform. For example, if our target is to have a real-time processing, then our neural network should be fast enough to process data at real time. So let's first talk about different network topologies that currently used in your network. The default topology, which you have discussed before, is called feed-forward network. In this case, the transformation from one layer to the following layer goes into only one direction, from input to hidden, then to output. There is also a recurrent network where data can move in forward and backward directions, or even to neurons in the same layer. This kind of feedback passes is useful in time series problems and control problems. This is an example of a single layer feed-forward network. We can have multi-layer feed-forward network, and you can add more or more hidden layers as well. In this section, we're going to talk about activation functions. The activation functions are used to transform the summed weighted input into an output, as you recall from previous lectures. So we have an input data A from A1 to AK and weights W. and then we multiply each input with the corresponding weight and sum all of them together and add the bias component, and the result is stored into Z. The value of Z is the weighted sum of the input, and it has a linear relation with the input. The activation function is used to add nonlinearity to the result, which help support implementation of nonlinear functions. The activation function also is used to facilitate the neural network training, as we're going to see in later lectures. In some cases, the activation function can be used to estimate the probability of certain output class, for example, in classification tasks. There are several popular types of activation functions that we're going to discuss in this section. Each one is used in some tasks. The binary step activation based classifier, and if the input is above certain threshold, the neuron is activated and the output is 1. Otherwise, the neuron is considered deactivated and the output is 0. The problem of the binary step activation function is that it does not support multi-class problems. It just produces 0 and 1, cannot produce anything in between. There is also some problems with the gradient. Since the gradient is 0, this causes some problem in the training process, as we're going to see later. The linear activation function is very useful in regression problem, in which case the output signal is proportional to the input signal. So the f of x equal c multiplied by x, where c is a constant. If setting c to 1, this is called identity activation function. A sigmoid activation function take any real value as an input and the output value in the range from 0 to 1. It is sometimes called the squashing, since no matter the input range is, the output all the time is limited to 0 and 1 range. This is also used sometimes in calculating probabilities, as we discussed before. One of the problems with the sigmoid function, it's not balanced, so the range of output from 0 to 1. And the other problem, it's the quick saturation it has, since if the input start to increase, the output will be saturated very quickly to 1 or 0. In order to solve the unbalanced problem, there is also a tanh activation function, which is very similar to sigmoid, but it has even balanced output in the range from -1 to 1. Since the output is zero-centered, the tanh is useful in several classification tasks. For example, in the recommendation system, when you are looking for like 3 separate output, like strongly okay, strongly not okay, or neutral. This is a very nice use case for the tanh function. And that's why it's usually used in hidden layer, as it helps in centering the data and make learning in the next layer much easier. The tanh also has some problem, which is vanishing gradient, that will be discussed in the training lecture. The radio activation function is one of the most popular functions being used at the moment. It is called ReLU for rectified linear unit. It has a linear relation between the input and the output when the input is positive. Otherwise, it saturates to 0 when the input is negative. One of the advantages of using the ReLU is performance advantage. since when there is many neurons deactivated because of negative values, the number of computations needed in the neural network is much less. However, the same thing causes a limitation, since for all negative input, there is always output of 0. This is called a dying ReLU problem. And this also affects the neural network training, as we're going to see. In order to solve this problem, a leaky ReLU activation function was introduced, which allows some kind of output when there is a negative input. There is many variants of the ReLU, and the ReLU, as I discussed, is very important activation function and used widely in many activities. The last activation function we'll discuss is a softmax activation function. This is very useful in multi-class classification, where we are interested in having a probability of the output belong to a certain class. The use of sigmoid function by itself is not sufficient. So the softmax activation function actually it produces a probability for each class. It has similar behavior like sigmoid, but it adds the probability calculation after that. So as you see, we have 3 output nodes, E1, E2, E3. So the softmax sum the outputs, and after that use this value as a total and estimate the probability of each class using this equation, exponential of zi over the sum of exponential of zi. So after doing the sum, it will simply do a division, and as such, instead of having just an output or having the probability of outputs, the combination of y1, y2, y3 is all the time equal to 1. Function. There are several rules, but here we can go over a summary of some of them. Activation function used in hidden layer is typically chosen based on the type of the neural network architecture. ReLU activation function is only be used in hidden layers, while sigmoid and tanh function should not be used in hidden layers because they make problems during the training. In regression problems, it's recommended to use linear activation function, while in binary classification, sigmoid, tanh should be fine. Multi-class classification, it's recommended to mix because it reduces the probability of each class. In multi-label classification, we can use either sigmoid or softmax. In convolution neural network, it's very useful to use the ReLU activation function. And in recurrent neural network, use of tanh or sigmoid is recommended. Now let's have few examples on a neural network. This is an example of an XOR neural network. So as you can see, we have 2 inputs, X1 and X2, and we have one output here. In between, we have one hidden layer that has 2 neurons or 2 nodes, one of them representing the mathematical OR of the inputs, and the other one represents the mathematical AND of the inputs. Combining those 2 nodes together as the output will produce the target XOR function. If you look closely at the input, so these are the weights for each connection, and these are the bias. So only difference between the OR and AND representation is actually in the bias. Let's have another example when we have multiple hidden layers. This is a very simple network. This is the input. Those are the bias and weights. And we are using sigmoid activation function. The weighted sum at this node is 4. and we're using sigmoid function as an activation function. So the output would be 0.98, and this output will be 0.12. Now, if you add another layer that takes this input, this output as an input, and with the weights shown, we'll have different values, and you can have another layer and different outputs. This neural network is called a transformation neural network. It just take input of two values and produce an output of two values, and we can call it f of 1 and minus 1 equal to 0.62 and 0.83. Our last topic that we're going to discuss today is the deep neural network. The deep neural network has many hidden layers, unlike what we have discussed. So you can have many hidden layers. As we discussed before, each layer has neurons, and neurons of each layer is connected to neurons from previous layer and output to following layer. Deep neural network can have different types of layers, which we're going to discuss later. Different types of connection between layers. You can have different number of layers, different number of neurons in each layer, and different types of activation functions. This is an example actually of a deep neural network which illustrates what each layer is actually outputted. So this is our input here, an image, and this network is trained to figure out what type of animal this is. And there are several hidden layers. The first hidden layer is actually useful in extracting edges of the input data. The second hidden layer combines those edges together to produce some kind of texture or partial object parts, while the top layer actually is producing the full object estimate, which can be with different probabilities. And the final decision, of course, will be to the best probability of the output. In this lecture, we discussed the artificial neural network. We talked about the deep neural network. We provided some neural network examples. In the next lecture, we're going to talk about the different layers in a neural network. Thank you very much.